we need to do an example. So let's do an example. I'm not sure if I have one from start to finish. Oh, I do. Let's do one from start to finish and see if we can accomplish all of these things. Here we go. For example. All right, x1 prime equals 4x1 plus 2x2. x2 prime equals negative 3x1 minus x2. And my particular solutions, and again, remember these are appearing by magic. So my particular solutions are x1 of t equals, sorry, hang on. Oh, sorry, okay. So x1 equals, we're gonna write this in column form. So solutions to this are going to look like two functions, yes? Solutions to this are going to look like two functions. So I've got a couple of particular solutions. So particular solution number 1 is going to be x equals 2e to the t negative 3e to the t. So that's my particular solution number 1. It needs to be two functions, right? It has to be two functions. A particular solution needs to be two functions. And we'll call that x1 because I'm going to have two of them. Particular solution number 2 is going to be, we'll call it x2. This is a vector, so it needs an arrow over it. And that's going to be e to the 2t and negative e to the 2t. The subscripts are easy to get confused. So you got to be careful about whether you have a vector and a subscript or not vectors. So in other words, for this first one up here, I have two solutions, right? x1 of t without a vector is 2e to the t, and x2 of t is negative 3e to the t without vectors. So if I take each of these, if I take their derivatives, if I plug them back in, I should get two equations that work out that balance. My second one is x1 of t equals e to the 2t, and x2 of t without vector arrows is e to the negative 2t. That's the way I'm writing these out. So since I'm looking for combining two particular solutions, a particular solution has two functions in it. Particular solution in this case has two functions in it because I've got x1s and x2s. Two solutions in a particular solution, or two functions in a particular solution. Okay, let's do matrix form first. So first of all, we wanted to do matrix form. That means I need my vector x, I need p of t, and I need my vector f of t. Those are the things that I need. I need my vector x. This one's easy. Vector x always stays the same. So this is just going to be x1, x2. Always stays the same in terms of however many things in it you need, however many functions. P of x comes from the coefficients. So reading across, or p of t, I'm sorry. P of t comes from the coefficients. There are no t's, there's just constants. So this is going to be 4, 2, negative 3, negative 1. Do we see where those are coming from if I read across? 4, 2, negative 3, negative 1. Those are good? We're good with those? Okay. And then my vector, little f of t. This is a homogeneous system, so this is just going to be 0, 0. So I can write this in matrix form. Everybody good? All good? All right, the second thing we were supposed to do is verify that a solution appearing by magic is actually a solution. Verify that a solution appearing by magic is actually a solution. So we've got two solutions appearing by magic this time. First, verification. So we want to verify that vector x1 is a solution. So in order to do this, I have a need to show that vector x1 prime equals P of t times vector fx1 plus vector f of t. That's my system of equations, and I'm plugging x1 into it. I want to make sure that my vector x1 is actually a solution. So I need to show that x1 prime, vector x1 prime, is P of t times vector x1 plus f of t. Okay, we're going to do this, and I want to see all of you at this point in time. Yelled at you. I yelled at you a lot at the beginning of the semester. I yelled at you an awful lot at the beginning of the semester. How do you verify a solution to a system of equations? Start on, Stuart.
Pick a side and write it down.
Yes, pick a side, write it down, and then what do you do after you pick a side and write it down? Start on one side, pick a side and write it down, then what? Then what do we do? How well did my yelling at you go? Go to the other side. Yes, thank you. So pick a side, write it down, do some math, get to the other side. Fingers 1 and 2. It's not up on my screen, but I want to be able to see all of you. Fingers 1 and 2. Left side or right side? Which side would you like to pick and write it down? 1 is left side, 2 is right side. Fingers 1 or 2. Left side or right side? What do we got? Lots of 2s. Thank you. All right, so let's go ahead and do this. If we are going to verify, we are going to have, so we'll label this as verification. I am going to have P of t times vector x1 plus vector f of t. Look, I wrote down the right-hand side. Exactly how the left-hand side appears. We'll see how my yelling at you went. Now I can start plugging some stuff in. So my P of t, reading across, is 4, 2, -3, -1. My vector x1 is 2e to the t, -3e to the t. And my vector f of t is 0, 0, because this is a homogeneous equation. Okay, multiplying matrices together. So if I multiply, I am going to get 4 times 2e to the t plus 2 times -3e to the t. If you want to jump right to multiplying, if you want to jump right to adding, that's fine. I can live with that. Next one, -3 times 2e to the t plus -1 times -3e to the t. Multiplying, remember how we multiply? If I simplify this, I'll multiply out and simplify all in the same step. That is 8 minus 6, so that is 2e to the t, and -6 plus 3, so -3e to the t. Is that good? Do I like that? Does that get me to the left-hand side? Is that vector x1 prime of t? Do we like this? Yes, yes, yes. This is vector x1 of t. So notice, please, I am writing down x1 prime of t. I started by writing down one side. I finished by writing down the other side and did some valid math in between. You should channel me in your dreams at night when you're thinking about how to verify these things. I want to hear my voice in your head. This is what should be happening with verifying. Okay, take a couple minutes, please, and verify that x2 is a solution. I'll write it out here. You write it down on your piece of paper. Verify that x2 is also a solution, please. I'm going to erase this verification so that I can do it all on the same slide. You're gonna need to have an idea of what x2 prime is equal to so that you know when you get there. So you're gonna need to just do a quick derivative. You can do it in your head, you don't have to write it out, that's fine. But you're gonna need to do a quick derivative so you know what the derivative is that you're looking for when you get there. In the first case, the derivative was the same as x1. In this case, it's different. So if you plug in, if you multiply out, you should get 2e to the 2t and negative 2e to the 2t. And that's your derivative. That's what you're looking for. If you go back up to x2 and think about what the derivative is going to be using chain rule. Okay. How are we doing? I'm going to stop sharing for a minute. How are we doing to this point? Give me a thumbs up. We're good? Yes? Everybody ready to move on to the next step? Okay, next step then. Here we go. So let's go back a slide. The next thing that I want to be doing is use particular solutions appearing by magic to create a general solution. But first we have to check if these are linearly independent using the Wronskian. So we've got two particular solutions. Let's remember how to set up the Wronskian and decide if these are linearly independent. So once again, our particular solutions are vector x1 equals 2e to the t, negative 3e to the t. Vector x2 equals e to the 2t, negative e to the 2t. And I want to decide if these are linearly independent. Are these linearly independent? So what I'm going to need to do is set up the Wronskian. It's just a 2 by 2. It's not a 3 by 3 this time, so we don't have to worry quite so much about the determinant. So the Wronskian of x1 and x2. In this case, I'll read across 2e to the t, e to the 2t, negative 3e to the t, negative e to the 2t, and I need a determinant out in there, sorry. So the determinant of that matrix, the determinant of 2e to the t, e to the 2t, negative 3e to the t, negative e to the 2t. Determinant of 2 by 2s is easy, just multiply in one direction and multiply back in the other direction. So 2e to the t times negative e to the 2t. And then I got to subtract, minus e to the 2t times negative 3e to the t. Remember that when you multiply, you add exponents. So my exponents are going to be e to the 3t. We've got negative 2e to the 3t plus 3e to the 3t. So that's just 3, or just e to the 3t. For linearly independent, thumbs up or thumbs down? Thumbs up equal to 0, thumbs down not equal to 0, identically. Equal to 0 or not identically equal to 0? Thank you, not. So that means I have to find a value of t that will work. Fingers, somebody give me fingers, a value of t that will work to make this not equal to 0. Fingers, 9, okay. Daniel has 9. Thank you for making class interesting. So this is not equal to 0 if t is equal to 9. And so therefore, this is not identically equal to 0, and therefore I get linearly independent. Okay, that's good. We like that. These two solutions are linearly independent, and so therefore we can combine them to make a general solution. Remember, this method, it's called the principle of superposition, only works if you have a homogeneous system of equations. Has to be homogeneous. So, principle of superposition. Principle of superposition. my general solution, and remember this is only for homogeneous systems. Only for homogeneous systems. Don't use it on a non-homogeneous system, it's not going to work. My general solution, X, this is my general solution. It's a vector. My general solution X is C1 vector X1, C2 vector X2 plus a bunch of dots, Cn vector Xn. In this particular example, it's just C1 and C2, but we're writing this out as generally as we possibly can. So general solution, vector X is C1 X1 plus C2 X2 plus bunch dots plus Cn Xn. We've seen this, it's been a little while, but you should be good at having seen this, not a problem. So in this case, for this example, here's my general solution, and then I'm gonna rewrite it because the book writes it in both of these ways, and I would like you to be comfortable with both. So here's my general solution in this one. It's going to be vector X equals C1 vector X1 plus C2 vector X2. That's just the principle of superposition, no big deal there. So this is going to be C1 times 2e to the t negative 3e to the t, right? C1 times that, plus C2 times e to the 2t negative e to the 2t. So C1 times my first solution, C2 times my second solution. I can combine that into one vector. So here's my OR. I can say X equals, reading top line, 2C1 e to the t plus C2 e to the 2t. I can multiply and add, right? 2C1 e to the t plus C2 e to the 2t. And then my second line is going to be negative 3C1 e to the t minus C2 e to the 2t. So I can combine into a single vector if I want to. Everybody's okay with that, right? And then, and now this is where the book sometimes switches, so I want you to be comfortable with both. Remember that a general solution to this system of equations is two functions in this case, right? X1, X2. That's a general solution. So we could also say, and these are functions, not vectors. They don't get vector arrows over them. X1 of t is the first one. 2C1 e to the t plus C2 e to the 2t. That's my first function. And then my second function, X2, is negative 3C1 e to the t minus C2 e to the 2t. Careful with the difference between functions and vectors. Be very careful of where you need vector arrows on top of something. So both of these are a valid way to write the solution. Putting two of them together in a single vector or writing them out separately. You can do it either way, putting them together in a column vector or writing them out separately. Either way works for a solution. The book tends to switch back and forth, and so that's why I want you to be comfortable with both of these so that you can tell, oh yeah, I wrote my answer this way, but the book wrote the answer that way. So I want you to be comfortable with both. Okay, that's steps 1 through 3. How are we doing on steps 1 through 3? Give me a thumbs up. This should look familiar. It's with matrices, right? But it's a lot of the stuff that we did back in chapter 2. Yes? Good. A lot of the stuff that we did back in chapter 2. Yes? Okay. So here's where we're at then. And we're not doing this today. We're actually not doing it tomorrow either. But where we're at is step number 4. Find particular solutions for a system of homogeneous equations. That's what we have to do. We have to get these solutions that appeared by magic and figure out what they are for real without magic. When we did that back in chapter 2, that was when we came up with the characteristic equation and the roots and all that fun stuff, right? That is going to be, what day is it? Monday? Wednesday. That is going to be Wednesday. Tomorrow, we are taking a small pause and doing this process with matrices and everything else for non-homogeneous systems. So tomorrow we're going to come back and say, oh, look, magic, bunch of stuff, non-homogeneous systems. And then on Wednesday, we're going to get into how do we do magic? How do we find these solutions? What's our bigger analog to the characteristic equation? Everybody kind of seeing the roadmap where we're going? Hopefully, if I've done well over the course of the semester, this should be familiar, at least the process and what's going on. The steps are different, the details are different, but the process should hopefully be kind of sort of similar. Yes? Yes? Okay. Questions. This is a good place to stop. One example working through. Anything for questions at this point in time? Awesome. All right then. Tomorrow, non-homogeneous systems. So if you are so inclined, I want to go back and review, 2.4, 2.5, something like that. If you feel like it, go for it. Otherwise, we'll work through non-homogeneous systems tomorrow. I will send out homework in just a couple of minutes. Otherwise, have a good afternoon. Bye, everybody. See you tomorrow.